All right, so this is Nwacc, Survey of the Universe, Lecture 17, The Lives of Stars, for Monday, March 30th, 2020. As you make your way through this video, please, please, please take notes. Pause the video now and go get your notebook. I'll wait. We do have both a classwork and a lab today. Both are available in Canvas. Simply click Assignments, and both the lab and the classwork will be visible under upcoming assignments. Classwork is due tonight, that is Monday night, and the lab is due tomorrow night, Tuesday. I want to caution you, the lab has a lot of math, so please don't just dive into it. Instead, redo the examples first. The relevant examples are Kepler's third law in Lecture 6 and parallax and magnitudes in Lecture 15. If you get stuck and ask for help, the first thing I will ask is, did you redo the examples? So, let's begin, as always, with poetry. Properties of the star on the HR. The left is hot. The right is not. The top is bright. The largest stars are the upper right. The main sequence spends the weekends fusing hydrogen into helium. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. All right, so today we will discuss the lives of stars from birth to death, and we'll learn that low-mass stars like our sun die quite differently than high-mass stars. We learned previously about the nebular theory, that stars form from a collapsing cloud of mostly hydrogen gas, a nebula. It turns out the galaxy is filled with gas. We call it the interstellar medium. Stars only form in places where the interstellar medium is dense enough and cool enough to collapse under its own gravity. It has to be dense, so there's a lot of mass and a small volume, so the gravitational force can be significant enough to pull the cloud inward. And it has to be cool because hot gas has a lot of thermal pressure that resists the inward pull of gravity. Consider a water vapor cloud in our atmosphere. If it has the right conditions to form a raindrop, you don't usually get one raindrop. You get lots and lots of raindrops. You get rain. Likewise, in places where the interstellar medium has the right conditions to form a star, you don't get one star. You get a rain of stars, a cluster of stars. So, stars are born in clusters, a few thousand at a time. When a star is in the process of forming, we call it a protostar. It contracts because of gravity. When the cloud was large, it had a lot of gravitational potential energy because each particle had a long distance through which to fall. But as it contracts, that potential energy is converted to thermal energy. In other words, the protostar heats up. It keeps contracting and keeps heating until the core of the protostar becomes hot and dense enough for nuclear fusion to begin. Once that happens, the core heats up even more and thermal pressure stops the collapse. A star is born. For a star like our sun, that contraction process takes about 30 million years. The more massive the star, the stronger the gravitation, so the less time it takes for the protostar to collapse. To review star birth, when a cloud is cool and dense enough, it fragments into thousands of protostars. Each protostar collapses under its own weight. The core heats up due to conservation of energy. Contraction continues until nuclear fusion begins, at which point the protostar becomes a star. So, how massive are these stars? There's a common pattern in astronomy. Small things outnumber big things. Small galaxies outnumber big galaxies. Small planets outnumber big planets, we think. Small comets and asteroids definitely outnumber big ones, and so on. Stars are no different. Most stars are very low mass stars, less than half the mass of our sun. As shown in this graph, for every 200 low mass stars, there are 50 stars like our sun, and only 11 stars with more than twice the sun's mass. So, what limits a star's mass? Radiation pressure. Light produces pressure. And that's strange to think about, right? If you shine a flashlight at me, would that beam of light exert a pressure that pushes me backward? Well, technically, yes. But the pressure would be too small to notice. However, the core of a high-mass star is so luminous, radiation pressure is significant. If a star has too much mass, its core will be too luminous. It will push the star's outer layers away. In other words, if a star is too massive, it will blow itself apart as soon as it's born. The most massive star whose mass has been directly measured by its gravitational effect on a binary companion is about 150 solar masses, or 150 times the mass of our sun. The most massive star whose mass has been estimated by computer models is about 300 solar masses. High mass stars are rare, so we have limited data on this upper limit. Come back in 5 years and that number may change. Low mass stars, on the other hand, are extremely common, so we have lots and lots and lots of data on the lower limit. The lowest mass stars can have about the lowest mass a star can have is about 0.08 solar masses. If a protostar's mass is less than that, its core will never get hot enough to complete the process of nuclear fusion, so it will never shine brightly like a star. We call such objects brown dwarfs. They are dim and difficult to detect, but they are numerous. So, to recap, star masses range from 0.08 solar masses up to a few hundred. Stars with too little mass can't fuse hydrogen. We call them brown dwarfs. Stars with too much mass blow themselves apart with radiation pressure as soon as they're born. Stars then are born in cool, dense, molecular clouds. One cloud will form thousands of stars, and star masses range from 0.08 to a few hundred solar masses. We tend to classify stars by their masses. Any star with less than 8 to 10 solar masses we call a low mass star. Any star above that we call a high mass star. The reason for this seemingly arbitrary cutoff is that low mass stars die much differently than high mass stars. So, how does a low mass star live its life? Let's begin the answer with a question. Write the answer down in your notebook. What happens when a star can no longer fuse hydrogen in its core? A, it cools off. B, it shrinks and heats up. C, its core expands and heats up. Or D, helium fusion immediately begins. Write down the answer. Without the energy released by nuclear fusion, the core cannot maintain its size. It shrinks under the weight of the star as the outer layers push inward. What happens when you compress a gas? You heat it up. So the core shrinks and heats up. Recall that if a star is still fusing hydrogen in its core, it is on the main sequence. Once it runs out of core hydrogen, it leaves the main sequence and bounces around the upper right corner of the HR diagram. The path it takes is called its life track. Once a low mass star leaves the main sequence, it swells up and becomes a red giant. Recall from lecture 14, the sun, that nuclear fusion in the core is a thermostat. If the core gets too cool, nuclear fusion decreases, the core shrinks, then heats up, and the core goes back to its normal temperature. Likewise, if the core gets too hot, nuclear fusion increases, the core expands and cools back to its normal temperature. But when the hydrogen fuel runs out, the thermostat is broken. there is nothing to stop the core from shrinking and shrinking and getting hotter and hotter. So hot, in fact, nuclear fusion begins to happen in a shell outside the core. Lots and lots of nuclear fusion with several effects. First, lots and lots of energy is released, so the star gets really bright. Second, the core is so hot, thermal pressure pushes the outer layers of the star outward, causing the star to swell up. It becomes a giant. Finally, since the outer layers are expanded, they cool off, even though the core is still much hotter than before. Since the outer layers are cool, the star shines mostly in the red and infrared wavelengths. In other words, when a star runs out of hydrogen fuel, it becomes a red giant. When this happens to our sun, the photosphere will swallow the orbits of Mercury, Venus, and Earth. So the core keeps shrinking and heating up. The star keeps growing and reddening. Eventually, the core gets hot enough to fuse helium into carbon. At this point, nuclear fusion has resumed in the core. So the thermostat is fixed. The outer layers therefore shrink a bit, which heats up the photosphere. Now the star has two regions of nuclear fusion. The core is fusing helium into carbon, while a shell around the core is fusing hydrogen into helium. We call this star a helium fusion star, sometimes called a horizontal branch star, because the stars line up horizontally on the HR diagram. So, how does a low-mass star die? Well, here's a thought question. Write down the answer. What happens when a helium fusion star's core runs out of helium? A, it explodes. B, carbon fusion begins. C, the core cools off. D, helium fusion begins in a shell around the core. Write down the answer. It's essentially the same thing that happens when the core ran out of hydrogen. The core shrinks and heats up, and fusion continues in a shell around the core. Only this time, there are two shells. The core itself has no fusion. It's just compressing and heating up. Outside the core is a shell fusing helium into carbon. And outside that is a shell fusing hydrogen into helium. Once again, the thermostat is broken, so the star gets more and more luminous. It gets brighter and redder. We call this star a double shell red giant, sometimes called the giant asymptotic branch. So right now, our sun is fusing hydrogen into helium. At the end of its life, it will turn helium into carbon, and at the very end, it'll turn some of that carbon into oxygen, but that's it. It takes higher temperatures to produce heavier elements, and the sun's core will never be hot enough to produce anything heavier than oxygen, well, at least not in significant amounts. Instead, when the sun is a double shell fusion red giant, its core will get hot enough to produce one or a few rapid bursts of nuclear fusion that push the outer layers of the sun out into space to form a planetary nebula, which has nothing to do with planets, sorry. The core then will be left behind as a dense ball of carbon and oxygen called a white dwarf. This is the Helix Nebula, a planetary nebula. The cloud is the outer layers of a dead star, and there is a white dwarf right there in the center. The video is too low res to see the white dwarf, but if you view the lecture slides on Canvas, you'll be able to see it. Since there's no fusion in the white dwarf, there's no energy released that can hold up the weight of the star, so it keeps getting smaller and more compact and more dense until the electrons themselves start bumping into each other. When too many electrons occupy the same space at the same time, they produce an outward pressure that stops the white dwarf from further collapse. By the time, we call this electron degeneracy pressure. By the time electron degeneracy pressure is able to stop the collapse, the white dwarf is so dense, a piece the size of a marble would weigh as much as a car. To recap, here is the life track of a star just like our sun. When the core is fusing hydrogen, it's on the main sequence. Once it runs out of hydrogen in the core, it swells up and becomes a red giant, burning hydrogen in a shell around the core. Once the core becomes hot enough to fuse helium, it shrinks again. When the core runs out of helium, it will swell up again to become a double shell fusion red giant. Rather quickly then, it poofs its outer layers into space to form a planetary nebula, leaving its core behind as a white dwarf. So here are some vocabulary words that would be good to take with you: main sequence, red giant, horizontal branch, and white dwarf. So, a low-mass star like our sun turns hydrogen into helium, helium into carbon, and briefly turns carbon into oxygen as it poofs its outer layers into space. Okay, that's cute. What about a high-mass star? Let's look at the life stages of a high-mass star. Like a low-mass star, it burns hydrogen on the main sequence. When its core runs out of hydrogen, it burns hydrogen in a shell around the core, and the star swells up, much larger than a red giant. We call it a red supergiant. While a red giant may be the size of Earth's orbit, a red supergiant may be as large as the orbit of Mars, or even Jupiter. It then burns helium on the horizontal branch, runs out of helium and becomes a double shell supergiant. So far, its life is similar to a low-mass star, except a high-mass star keeps going. Carbon fuses together to form neon, sodium, oxygen, magnesium. More and more shells form around the core, like layers of an onion, each layer fusing heavier and heavier elements until... Let's pause for a moment and recap how elements on the periodic table are formed. Hydrogen was formed a fraction of a second after the Big Bang, the explosion of space-time and energy that began our universe. Hydrogen fused into helium in the first few minutes after that. Everything else is made by stars. Main sequence stars fuse hydrogen into helium. Horizontal branch stars fuse helium into carbon. High-mass stars then fuse carbon into other elements like neon, oxygen, magnesium, and sodium, which then fuse to form even heavier elements like silicon, sulfur, calcium, and eventually iron. Iron kills the star. Iron is the executioner of a red supergiant star. Why? Because elements lighter than iron release energy when they fuse. Radiation pressure from nuclear fusion holds up the weight of the star, but iron and elements heavier than iron do not release energy when they fuse. They absorb it. So, when iron is manufactured in the core, it sucks up the luminosity of the core. Within seconds, the core goes dark. Quite suddenly, there is not enough radiation pressure to hold up the star. So, the full weight of a red supergiant star, 10 times the mass of the sun or more, goes into freefall on the core, collapsing the core. The full weight of a red supergiant star smashes into the core at nearly the speed of light. Boom! When the full weight of a red supergiant star smashes onto the core at nearly light speed, the outer layers bounce off the core in a shock wave that can take out a solar system, a supernova, an exploding star, an explosion that's as luminous as an entire galaxy. And what happens to that core? The outer layers smash the electrons right into the protons, combining them into neutrons, leaving the core behind as a neutron star, a giant ball of neutrons. A neutron star is essentially a giant atomic nucleus with the mass of a star compacted down to the size of Bentonville. And if the star was massive enough, the neutron star itself will collapse into a black hole, an object in space with so much gravity it pulls space and time with it as it spins, and from its grasp nothing can escape, not even light. And during this supernova, nuclear fusion makes lots and lots of metals like iron and nickel. Earth's core is made of iron and nickel, and those metals were made during a supernova when a red supergiant exploded. This is the Crab Nebula, the remnant of a supernova that was reported by Chinese astronomers in the year 1054. This is supernova 1987A, so called because it was the first supernova discovered in 1987. So, the core of this exploding star is left behind as a neutron star. Since it's not fusing, there's no radiation pressure to prevent it from collapsing, so it keeps shrinking, getting more and more compact until the neutrons start bumping into each other and producing an outward pressure called neutron degeneracy pressure. However, in rare cases, the neutron star is so massive, its gravity is able to overcome neutron degeneracy pressure, so it collapses into a black hole. When iron and elements heavier than iron fuse, they absorb energy instead of releasing it. But when a star explodes, there is plenty of energy to go around. So there is a lot of fusion. Iron, nickel, and zinc, among others, get manufactured in large amounts. So, a low-mass star fuses hydrogen into helium, helium into carbon, and at the very end of its life, carbon into oxygen as it poofs its outer layers into space, leaving its core behind as a white dwarf. A high-mass star fuses heavier and heavier elements until it makes iron, which triggers a supernova. A star's life stages are determined by its mass. So, where do elements come from? The Big Bang made hydrogen and helium. Low-mass stars make helium, carbon, and oxygen. High-mass stars make everything from helium up to iron. Supernovae make elements that are near iron on the periodic table. But what about the really heavy elements, the rare and valuable elements like gold and silver and platinum? How are they made? It turns out the really valuable elements are made when two neutron stars collide. We call that a kilonova, and those elements are in purple here. All right, we made it through the exploding star, so once again, let's do some poetry. When the sun's core depletes its store of hydrogen fuel, the sun will swell and cool. A red giant it will be until it finally poofs its atmosphere out into space, leaving a white dwarf in place. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. As always, please download the lecture slides for the summary slides, and don't forget the lab and the classwork. See you next time.